it's chlorine and light. So I'm going to convert that problem very quickly into my line angle drawing. And my line angle drawing is going to look like that. And so this guy is called pentane in a line angle drawing. How many sets of equivalent hydrogen do you have in pentane? Sets of equivalent hydrogen are there in pentane? Anybody knows? My chemistry students better know this. All right, so 1, 2, 3, 4, 5. 1. Anybody says there's one set of equivalent?
I say it's 3.
How many types of carbons do you have in pentane? Types of carbon. There are 2. All right, so there are 2 types of carbon. These guys here at the end are called your primary carbons. So those 2 are the same. These are primary carbons. Primary carbons have primary hydrogens on them. These guys should all be the same, and they are. So all of these chicken feet over here, okay, these are all primary carbons with primary hydrogens. All of them are equivalent. If you replace any one of them for a chlorine, it doesn't matter which one it will be. They're saying that it's chlorine and light. So if you replace any one of those for a chlorine, it doesn't matter which one it is, your compound will be called 1-chloropentane. So then you say all those 6 hydrogens are equivalent. All 6 are equivalent. We need this for spectroscopy that starts, well, possibly today. How's that? All right. So 6 hydrogens are equivalent. We're going to go ahead and label them all hydrogen pink, and they're all equivalent. All right. So the replacement of any one of them leads to the same product, which will be called 1-chloropentane. You must write the number 1 because that chloro could be in different places. As I move inside the chain, we would call all of these in blue secondary carbons, right? We will call all of those secondary carbons. But my question to you is, are all those secondary hydrogens equivalent? Meaning, some people say yes, some people say no. If I remove any one of these here, there are 4 there. If I remove any one of those and I replace it for a chlorine, the compound that I generate is that and that. Are these compounds the same or different?
The same.
They're the same. Then you go back and say, hey, by the way, all of these 4 hydrogens are equivalent. They will all go ahead and generate 2-chloropentane. Okay? Everybody okay still? And now I'm left with the carbon in the center. The carbon in the center is also a secondary carbon. And it also has secondary hydrogens. But when I remove any one of those, if I were to remove any one of those from here, any one of them, I take away one of them and I replace it with a chlorine, I end up generating a different compound altogether. So then we're saying that that carbon is only equivalent to itself, and those hydrogens are equivalent to themselves. So the compound pentane has 3 sets of equivalent hydrogens. The sets of equivalent hydrogens really lead you to believe immediately the set of isomers that you can generate from any one compound. So if from the beginning you knew that there were 3 sets of equivalent, you would have immediately known that you could have possibly 3 different types of chloropentenes as product. Is everybody okay with there? So this guy leads to your 3-chloropentane. As I go on to this, through this, not only do you see that you have 3 possible constitutional isomers, is everybody seeing that these are constitutional isomers, but you can also lead to some stereoisomers. Which of these 3 could have stereoisomer? Ignore him, he doesn't live anymore. We're gone. Which of those 3 have potentially stereoisomers? Can 1-chloropentane have stereoisomers?
No.
No, That carbon here is achiral. So there's no stereoisomers there.
The 2-chloro?
The 2-chloro, yes. So the 2-chloro obviously is got a chiral center. So yeah, that one could be your R and your S. And the third would be considered
Achiral?
achiral or symmetrical. That's another criteria to find if you have chirality. If there is symmetry, there's no chirality. I'm the same on both sides. But that's really not the question. All right, so the question is, what would be the major product of this reaction? Is there a major and minor product, and why? Is there major and minor, and why? Okay, so what is the type of chemistry that is occurring here? The reaction of chlorine and light and the alkane.
Chlorination,
What was that
bromination.
called?
Chlorination, bromination.
It was the chlorination of alkanes. Do we remember the mechanism of a chlorination or bromination? They're the only two. The free radical, right? So it was free radical. So when you go into free radical, the first thing that happens is that you cleaved the chlorine homolytically, right? So you started out the reaction like this, cleaving the chlorine. Oh. Okay, by the way, I haven't spoken for a long time, and I haven't written for a long time. I was on vacation like you guys were, so even us, we get a little rusty. All right, so here we go. The way that we cleave this was like that, right? It was that kind of a cleave that you created then the chlorine radical, and then we got sloppy, and we call it the Cl dot. And the Cl dot went and generated carbon intermediates. The carbon intermediates that we have generated are these. That, and that, and that. They're not all equal. These are primary radicals, while these are secondary radicals. Secondary radicals are more stable intermediates than primary. So the stabilities of free radicals are like this. Something that we have to memorize, and I think many of you remember. So stability of free radicals, the tertiary is more stable than the secondary, more stable than the primary, and much more stable than the methyl. So needless to say, if somebody said, what is the major product? It will be the 2-chloro and the 3-chloro. The 1-chloro, it's almost non-existent, by the way. It's very difficult to make a primary radical. But if they say draw all possible products, is everybody following? We're going to have a different layers of that. If they ask draw all possible products of reaction, possible 1-chloropentane, 2-chloropentane, 3-chloropentane, what are the majors? The secondary radicals. Is everybody okay? All right, we'll go to number 2, and they want you to do 1-ethyl cyclopentene. Okay, so 1-ethyl cyclopentene. So cyclopentene is this. That's cyclopentene. And on carbon 1, you can put the ethyl. That one may or may not be necessary. Okay, but that leads us to a different type of an alkene. What type of an alkene is this? Tri-substituted alkene. Is everybody hearing? We call that tri-substituted alkene. Your choices of alkenes are tetra. So here's the stability of the alkenes. Stability of alkenes. Based on heats of hydrogenation. Okay, stability of alkenes based on heats of hydrogenation. I call this tetra. So we went like this. Tetra. It's more stable than tri. More stable than trans, di. More stable than gem, di. More stable than cis, di. More stable than mono. Sorry for the abbreviations if this is your first time you're hearing this. We'll go ahead and try to put some structures with this. That's the stability of the alkenes, okay? A tetra-substituted alkene looks like this. So your tetra-substituted alkene looks like this, where you have all of that. So the R's can all be the same, or or they can be different, but this will be a tetra substituted alkene. I'll give you an example of one and you'll try to name it, all right? So we'll give an example of one and try to name it. So let's go this way. Oh my gosh. Ah, that's why we went with pencil. All right, that's better. Can you name it? Oh no, I have to add something to it. Sorry. Now I'm good. Promise. That's what happens when you teach on the fly, you know? I am.
Oh, okay.
Yes, I am. Thank you. In a whole different way of asking. Because what do you want me to do with this? Can you name it, please? Do we have a name?
Wouldn't it be 2,3-diethyl hextuene?
Say this again. I'm sorry. I have. You guys does anybody know what a transistor radio is or was? Like, have you heard of a transistor radio? Like bad signal, like you go. That's how my ears are going.
Wouldn't it be 2, 3, right?
From here.
No, I think it'd be,
You don't stop counting from here to get 7.
Say
No.
2,3-diethyl hextuene?
yeah.
All right. So that's what I'm hearing. 2,3-diethyl hextuene? I don't know about that. All right, so let me count.
Yeah, because you're gonna,
1, 2, 3,
give the
4,
lowest priority
5,
to the
6,
alkene.
7. So 1, 2, 3, 4, 5, 6, 7.
but you give the priority to the alkene, the lowest number. No.
All right. So I'm gonna. I'm sorry that everybody seems to be going a different direction here, but let me try this again. Okay, so the alkene needs to be part of the longest chain, no matter which way you go. So there's really actually 4 ways of starting. We could have started here and made that 1, 2, 3, 4, 5. Not good. You're fine. 5. You could have started here 1, 2, 3, 4, 5, 6. You could have started here 1, 2, 3, 4, 5, 6. Or you could have gone this way 1, 2, 3, 4, 5, 6, 7. So I'm going to go that way. And if I go that way, like that, then the other 2 remaining are substituents. So now the way to go is 1, 2, 3 or 1, 2, 3, 4. I have to start from here. The alkene has to have the lowest number. So the alkene begins on 3. So the name for this guy is going to be 4-ethyl, okay, and then 3-methyl. And then the newest nomenclature, hept, 3-ene, that's the latest, or the older one, where it was 4-ethyl, 3-methyl, 3-heptene. So those are the 2 options. And this will not give you all the points, okay? Because obviously we have to look at where do you want me to put these groups, right? Is it E or Z? It's in E or Z. We're looking down this way. So ethyl has higher priority than the methyl. So up here is high, and up here is high, right? And everybody remembers how to do this. So this one would have to get the Z, 4-ethyl, 3-methyl, F3. So that will be the name. And that we call a tetra-substituted unsymmetrical alkene. Tetra-substituted unsymmetrical alkene. Is everybody okay? Okay, a tri-substituted alkene then would look like this. So your tri can look like that. Your trans dye will look like that. Everybody, that's it, trans dye. Your gem dye looks like that. You can add more things to it, right? You can add more things to it, but you know, we're making it simple here. Your cis dye looks like that, or the other way up, right? So it could be up or down. And then your mono, well, it all started with the mono. Mono, by the way, monkey in Spanish. You learn one new word now in Spanish, mono, monkey. Mono, that doesn't have anything, it's ethene, so you started with ethene. So that's the stability of the alkenes. When I come back here, and I ask what type of an alkene is this, then you can see that you're substituted to 1 carbon, to 2 and to 3. There's a hydrogen here that we're not seeing that we're going to go ahead and draw. A tri-substituted alkene has regioselectivity. Regioselectivity. There's an area of the double bond that will be most likely to accept an atom. All right? So when you're adding HCl to this, right, we're adding HCl in presence of ether. In presence of ether, who's the nucleophile? Who's the nucleophile here? Who starts the reaction? Who's higher in electrons right now? Who's richer in electrons? The pi bond. Okay, so the reaction begins like that. I am unsaturated. I want electrons. So I'm going to go after you, and you're going to break heterolytically, and you're going to generate a carbocation. Okay, the gentleman's name was called Markovnikov. Markovnikov says when you're adding an unsymmetrical reagent to an unsymmetrical reactant, unsymmetrical and unsymmetrical, you will always generate the most stable carbocation. In plain English, we call this the rich gets richer. I already had a carbon, I already had a hydrogen. If I take in your blue hydrogen here, this will generate the tertiary carbocation. Stability of carbocations go like this. Stability of carbocations. Oh my gosh, it's so much easier to start teaching Chem 4 than Chem 3. So a tertiary carbocation is more stable than a secondary, more stable than a primary, and much more stable than a methyl. You're never going to make a methyl or a primary, but that's quite okay. We're still putting the stability order. So from the very beginning, your carbocation will be the most substituted carbocation, which is the tertiary, okay? And now the chlorine comes in. The chloride now will be your nucleophile. It goes in, and your product looks like this. So your chlorine came here. Your product then is called 1-chloro, 1-chloro, 1-ethyl, cyclopentane is the name for your compound. Is everybody okay with it? Right, everybody knew that this is the orientation. People knew that this was the product that you were going to form? Yes?
No.
Over here? People knew that? Yeah?
One.
Yeah? All right, let's take a look at number 3.
Because the ether was just part of the solvent. So
Ether is the solvent.
That's only
So
throwing me off.
ether is the solvent. Oftentimes,
What pink sheet is this?
the solvents of choice are either ethers or peroxides. If it is ether, then you're going through a Markovnikov carbocation. If it was a peroxide, it's almost always going to be a non-Markovnikov addition, yes, or anti.
Oh.
Very good. Okay, what happens with number 3? What are we gonna do with number 3? Do you wanna try to do these now a little bit by yourself? How about 3, 4, and 5 on your own? So we can go a little faster. 3, 4, and 5 on your own. I don't wanna bore anybody to death here.
Oh, here we go. The dial.
Dial. It's thin dial, right?
ETC chemistry, yes. That just breaks it. Which one? Yeah, the dial.
You can go along off and then you put the orange.
Yeah, that's what
Is it wedges or more wedges?
it's in. It's in chemistry.
So just put the wedges.
I would do it.
Did you draw it out or you just did it?
I did lining. It's still right though. Where's H?
That's dehydrated. That's hydration. You just make it up.
One, two, three. Whatever.
4. Alcohol.
Just make it alcohol. It's hydration.
It's a romantic language, so it has
You
a
know,
Go on
the
the
substitute.
secondary or tertiary.